Hey guys, welcome to another session on Math for Data Sciences. Now that we have a good understanding of what a continuous distribution represents, so basically the values of a continuous distribution could range in a continuous scale and could have infinite number of values between any two possible values of the distribution. Now, the first distribution which we'll be looking at here is called a continuous uniform distribution. So if you remember, we also had a uniform distribution in the case of discrete distributions. So we looked at discrete uniform distributions where we had a lot of values like A, B, C, D, and each one of these values had an equal probability. Now let us say if there are n values, which is n equal to 4 in this case, what the probability for each value was calculated as 1 upon n, which is 1 upon 4 in this case, in the discrete case, which meant px equal to a is 1 by 4, px equal to b is 1 by 4, and so on. Now, in the case of continuous distribution, since there are multiple or infinite number of values which are possible for the distribution, what we do is we create a range in which the uniform distribution is defined. So let us say we take two values on the x-axis, let us say a and b, where b is clearly greater than a. Now we create for a uniform distribution, the probability value has to be equal for each value in the distribution. Now let us say that value is, let us say k here. Then we define the probability distribution as ranging from a to b. So this particular line represents the probability density curve for a continuous uniform distribution. So if you remember, in the previous session we looked at an example where we were looking at an exponential distribution, and in that case the distribution shape was given something like a inverted curve, which is not the case here because we want the distribution to be equal for each value in the range. The range here is from a to b. Now, since this is a uniform distribution, how would we define the probability density function for the same? So we'll look at PDF for a uniform distribution. Now clearly the PDF defines the probability value or the value of the function for each value of x. Now since you can see the value of function here from the graph is k, which is a constant, that is why it's a uniform distribution. For each value of x from a to b, we define fx equal to k in the range from a to b. So this is the required PDF for a continuous uniform distribution. Now how do we find the value of k here? What we do, we use the property of probability that sum of all probabilities should be equal to 1. Now from the previous session we know how to compute the probability from a probability density curve. What we do is we simply calculate the area under the probability density curve. Now to calculate the area of this particular shaded rectangle, what we do is we look at b minus a multiplied by k. So this is the area of the shaded region, which is the area of the rectangle with base of b minus a and height of k. This should be equal to 1 since the total probability is always equal to 1, and therefore k is nothing but 1 upon b minus a. Thus we get the PDF for a uniform distribution as fx equal to 1 upon b minus a, where x ranges from a to b. So this is how we get to the PDF of a uniform distribution. Since the distribution is uniform, the values of probabilities for each value of x or the random variable x from a to b is equal, and it is equal to 1 upon the difference between the maximum and the minimum value of the distribution. So this is regarding it, the PDF for the uniform distribution. Next, we'll be looking at how to compute probabilities for a x range. Now let us say what we do is we consider a uniform distribution in the range, let's say 3 to 5. So A is equal to 3 here and B is equal to 5. Therefore, the probability mass function would be 1 upon 5 minus 3, which is 1 upon 2, that is 0.5 in the range 3 to 5. Now note that this probability density function is not giving the probability for x at any x value. So if you remember from the previous session, if we ask someone what is px equal to 4, let us say, it is still approximately equal to 0, since this is a continuous distribution and there are infinite many values of x between 3 and 5. So there are infinite values here, and therefore the probability, exact probability of a particular x value is always approximately equal to 0, since there are infinite many possible values in the given x range. So what we do for continuous or any continuous distribution is we calculate the probabilities for the random variable to lie in a particular range. So let us say we have to calculate the probability of x random variable lying in the range from 3.5 to 4. So what we do, if we go back to the chart here, we call this now as 3 and this becomes 5, and we are looking at a value of, let's say, 3.5 here and 4 here. Now if you remember again, to calculate the probability for this range, we simply calculate the area in this particular region here. So now the new base becomes 4 minus 3.5, while the height is still the same, k. So this is 0.5 into height, and height we already know is 0.5 as we derived here. So we get the required probability as 0.25, which makes sense since this is a uniform distribution and we are taking 1/4 of the total range. Therefore, the probability should be 0.25 here. Now, continuous uniform distribution is like very easy distribution, as you can see. Therefore, all the concepts to derive different metrics from the PDF of a continuous distribution is easy to explain, and that is what we are going to do here. And then using the same concepts, we'll be able to derive these metrics for other complex distributions in the future sessions as well. Now, we know how to compute the probability for a particular range of x range values using the area under the PDF. Now, think what here it was easy to calculate the area since this is a simple rectangle, but let us say we had an exponential distribution like our earlier example, then it would have been a little tricky because we don't know what the area of this particular shape is, since it would be something like this kind of an area, and we don't know how we calculate the area for this kind of a shape. So what we do, instead of using the area to calculate the probability for the uniform distribution itself here, we'll use something called an integral method to calculate the probability, like we saw in the previous session as well, how we compute the probability for a particular x range. So if you remember, we simply integrate the PDF in the given range, which is 3.5 to 4, to get the required probability, and this is given as 3.5 to 4, and the probability mass function again is already defined as 0.5 above. Now the integral of a constant is simply the variable itself, which is x here, and we put the limits from 3.5 to 4, which means 0.5, 4 minus 3.5, which comes out to be 0.25. So one now don't have to really worry about how we are getting the integral of 0.5. So we'll be putting up some maybe formula sheet in this lecture for basic formula for integration. But you just have to remember that we integrate the PDF in the required x range to get the probability for that particular x range for that particular PDF. So this is how we calculate the probability for x to lie in a particular range for any probability density function or any PDF function here. Now this is regarding probability calculations. Now if you remember, we looked at a couple of metrics, mean and variance, while we were looking at discrete distributions. So that is exactly what we are going to look here as well. So if you remember, the mean was calculated as the expected value of x, and it was calculated as summation of the value of x with their corresponding probabilities. So we'll use very similar method, but the summation, because there are continuous values here and there are infinite many values, we replace the summation with an integral here. And how we do that? We use the integral sign. We still put x, and instead of PMF, we are using the PDF here, since this is a continuous distribution and we are integrating with respect to x. So now, and we do that in the whole x range. So we do that in the whole x range. Now let us say we are again given a distribution u a to b. So this is a uniform distribution from x equal to a, the smallest value, to x equal to b, the largest value of the uniform distribution. So for this, we calculate the mean value as integral a to b, and the so we again put the variable x here, so this x. Now fx was defined as 1 upon b minus a, and we put dx here. So we can bring out the constant 1 upon b minus a integral a to b x dx. Now if you remember, the integral of x is given as x square upon 2, and we put the limits from a to b here, and we still have this constant b minus a. Now this could be written as 1 upon b minus a multiplied by b square minus a square upon 2. Now b square minus a square could be written as b plus a, b minus a, and we are still left with b minus a into 2. So this is, so I have used an algebraic identity here, which is x square minus y square equal to x minus y multiplied by x plus y. So you can just expand it and even check it. You will get x square minus y square from this particular product of these two functions. So we cancel out b minus a with b minus a here, and we are left with b plus a upon 2, which is actually the middle value of the uniform distribution. So if we had taken this particular case here, where the value was ranging from 3 to 5, the mean would have been equal to 4 in this particular example. So the mean, once again, is computed as the integral of product of the random variable x with the corresponding PDF, and the integral is calculated over the whole x range for that particular distribution. So now that we have the mean calculated as b plus a upon 2, which is the center value. So we define this for x a to b. So this is the middle value of the distribution. Now similarly, we can calculate the variance of the random variable x. So if you remember from the discrete case, we were calculating it as expected value of x square minus the square of mean. We'll still use the same method. So for expected value of x square, we again, instead of using summation, we use integral in the whole range a to b. We use x square fx dx minus mu square. So mu is already calculated. We can use that value directly here later on, and we integrate this a to b x square upon b minus a, which is fx, with respect to dx minus mu square. Now the integral of x square is x cube upon 3, and we put the limits from a to b, and we have 1 upon b minus a minus mu square. Now this could be written as b cube minus a cube on 3 b minus a minus mu square. Now again, using an algebraic identity, so I'll just write it here. X cube minus y cube is nothing but x minus y, x square plus y square plus xy. So this can be written as b minus a, b square plus a square plus ab upon 3 b minus a, and once again we'll just put the value of mean here, which was b plus a upon 2. So this becomes b plus a whole square upon 4, since we are squaring the mean here as well. Now once again the b minus a gets cancelled out, and we are left with b square plus a square plus ab whole upon 3 minus b square plus a square plus 2ab upon 4. So we just opened b plus a whole square as b square plus a square plus 2ab. Now taking 12 as the common denominator, we have 4b square plus 4a square plus 4ab minus 3b square minus 3a square minus 6ab. This becomes a square plus b square minus 2ab upon 12. This can be written as b minus a whole square upon 12. So this is how we get to the variance of a uniform distribution which lies in the range of a to b. So variance of this is x and this is actually u. So variance of x is given as b minus a whole square upon 12, while the mean was given as b plus a upon 2. So this is how we define or derive the variance and mean of a uniform distribution. Now we have looked at how we can get to probabilities for any x range for a uniform distribution, and we have also been able to get to mean and variance of the uniform distribution. So now we'll move on to the next metric. So we'll be looking at something called a CDF of a random variable. So till now we have looked at PDF, which is probability density function, which gives you the value of the function which we had here as a uniform distribution. So this function is called the probability density function, and the CDF is nothing but it's called the cumulative distribution function of a random variable. Now what cumulative distribution function tells us, it gives the probability of random variable x taking a value less than equal to some value small x. So for example, let us say, so if you remember, we denote the PDF probability density function as small f and x, but we denote the cumulative distribution function as capital X, and this is defined as px less than equal to x. So the cumulative distribution function, as the name suggests, cumulative, we are cumulatively adding the probabilities for all the values of x which are less than or equal to particular small x value for which this particular function we are calculating. So what we'll do here is, this will become more clear with an example. So what we'll do here is, we'll again take a uniform distribution from a to b, and we'll try to calculate the cumulative distribution function for this particular distribution given here. So we already know x less than equal to x, and we already know how we can calculate the probability for this particular range of x. So this range is actually nothing but from a to some small x value. And why we are taking a? Because the value of probability px less than a is anyway 0, since the distribution is only defined for x greater than a. Therefore we start the integral here from a and we go till some random small x. Once again we have fx dx. So we integrate the PDF from in the given x range to get the required probability. Therefore we get fx here, a to x 1 upon b minus a, which was the PDF for the uniform distribution, and this comes out to be x minus a upon p minus a. So this is how we get to the CDF of a uniform distribution or a cumulative distribution function of a uniform distribution. And once again, this is defined for x less than equal to a less than equal to b. Now let us say, just to check things, what we do is we calculate the value of CDF at b, which is the highest value, and we see p minus a upon b minus a is 1, which makes sense because we already know px less than equal to b is 1, since b is the maximum possible value for the random variable x. So this is how we get to the CDF of the uniform distribution.